So Laplace transform of convolution. And you'll know why we need convolution from this Laplace transform. Okay? So Laplace transform of f star g, okay, that's f of s times g of s. Or it's Laplace transform of f times Laplace transform of g. This is really important, okay? They are really multiplication in S domain. Okay? Multiplication in S domain means convolution in T domain. That's that's the importance of this convolution. We need multiplication operation in S domain, right? And it happens many times. It always happens. Multiplication of S functions in S domain, then that's simply convolution in T domain. Okay? So we knew that the plus operation in S domain, right? The partial fraction, something over S plus something S, right? So that's the plus operation, and we have exponential multiplication. If we multiply exponential function in S domain, that's time shift in time domain, right? And if there's a multiplication in S domain, that means convolution in time domain. Okay? So this is important, So I'm going to give you one example, all right, of how you use the convolution, Laplace transform of convolution, okay? So let's say a given function, h of s, is 2 times omega s over s squared plus omega square and square of this whole term. You can decompose this into the multiplication like this. 2 times omega over s squared plus omega square times s over s squared plus omega square. Correct? You can decompose a big complicated function into a more smaller form, right? Primitive form. Then you could do the inverse Laplace transform of big H, and the inverse of, and 2 comes out, okay, 2 times. You can take the 2 out immediately, right? 2 times inverse Laplace transform of omega over s square plus omega square times s over s square plus omega square. Okay? And each one is, this is what? Sine omega t, right? This is cosine omega t. Then what? So h of t is 2 times sine omega t star cosine omega t. Y double prime plus 2 times y prime plus 2y is sine omega t. Okay, y initial conditions are 0. Okay, so since the initial conditions are all 0, so s squared plus 2s plus 2 times big Y is sine is omega sine s squared plus omega square. Okay, so Y is omega over s squared plus omega square times 1 over s plus 1 square plus 1. Okay? All right. So Y is inverse Laplace transform of Y, which is inverse Laplace transform of s squared plus omega square times 1 over s plus 1 square plus 1. Okay, so we are using the convolution. So that's sine omega t convolute e to the minus t times sine t. It's actually example 5 on page 235. Sorry. Okay. All right. So I'm gonna solve this using convolution concept. Plus 3y prime plus 2y and r of t. Okay. R of t is same thing. 1, 2, 2, 0 otherwise. It's a square function. Same thing. And initial conditions are 0. So s squared plus 3s plus 2 times y is r of s. Okay? And let's take this. So it's a partially 1 over s plus 1, s plus 2 times r, right? So it's s plus 1 minus s plus 2 times r. Okay? And inverse is inverse Laplace transform, which is minus 1 over s plus 1 minus 1 over s plus 2. What? Convolution. Okay? I don't even, touch, R. Because I knew that, it's a convolution, and simply, this is very simple function, right? Okay. So, so this is e to the minus t from the table, right? Convolution r of t. I'm just going directly to the definition of convolution. So e to the minus t minus tau minus e to the minus 2t minus tau times r of tau d tau. I know that this is very simple function, so I'm shifting the other one. Okay? All right. The calculation. Before you do the calculation, let's draw. Always try to draw the graph, okay? So that you can more visualize, the things, okay? So this is it. That's the input, 1 to 2, okay? And if you draw this function, you need computer to really draw it, right? But anyway, that's this. So exponential function, so that's this function. Okay? And that one moves. Okay? It's the same concept. It moves. Okay? And it never goes to 0, because since this is exponential, if you draw that, it never goes to 0. Okay? So it's continuous. So let's try to move it. All right. This is t, and there's no end, there's no tail, right? It's infinity. Okay, but we have the same stuff. So this is the area, right? And that changes, right? And you see, there's no tail for this function, right? So so we have two regions, okay? 1 and 2. Before that, that's all 0, right? Okay, that's what you have in mind. So the first one is t is less than 1. That's y is 0, right? T is less than 1. It's all 0. Okay? And t is 1 to 2. Y of t is the head leading the upper limit of the integration, right? Same. So 1 to t, because from 1 to t, from here to here, right? That's the integration region. So e to the minus t minus tau minus e to the minus 2t minus tau times 1 d tau. And that's e to the minus t minus tau minus e to the 1/2 e to the minus 2t minus tau from 1 to t. Okay, if you put t's, it's 0, right? So it's e to the 0 minus 1/2 e to the 0 is 1/2, right? And minus e to the minus t minus 1 plus 1/2 e to the minus 2t minus 1. So this one is 1/2. Okay? And t greater than 2, the head, starting to leaving the, square, okay? So its head, starting to leaving, okay? The 2, so it's always 1 to 2, right? Integration is always 1 to 2. So it's constant, region of the, integration, right? So y of t is 1 to 2. Okay, same thing. It's the minus t minus tau minus e to the minus 2t minus tau times 1 dt, d tau. Okay? If you calculate it, that's this one. T minus 2 minus 1/2 e to the minus 2t minus 2 minus e to the minus t minus 1 plus 1/2 e to the minus 2 t minus 1. Okay? So we have the same, exactly the same, answer with the previous one. This one and that one.